Hi, I'm Mike Stanzik and this is Digital Electronics Classroom. Thanks for joining us today. In today's video we're going to be talking about Kirchhoff's current law, one of the foundational laws for analyzing circuits. In essence, it says that the current that enters a node is equal to the current that exits a node. And this is built on the premise that in steady state, in equilibrium, that we can't have any gain in charge at the node or loss in charge at the node, because that would change the voltage, the node voltage, and that would put the circuit into a state of non-equilibrium, non-steady state. So once it's reached steady state, the amount of charge that is in that node at any given time is staying constant. So any flow that's in is equal to the flow that's out. In this video, we're going to look at the definition and then a couple of examples of what we're looking for when we're solving using Kirchhoff's current law to do some analysis. So let's get started. So we have Kirchhoff's current law, or KCL. And before we get started, I want to draw a little picture here where we have a couple of resistors and this section here in the middle. And this section here in the middle, which is a junction of wires, I like to box here, and we call this thing a node. And a node is a connection between circuit elements. And it includes all of the wires up to the elements. So we can see here that when I boxed this node, I moved it all the way up to this bottom resistor, this right resistor, and this left resistor. So that whole thing is what we would call the node. And we're looking at a little section of the circuit, so there actually be a node here on the left, a node here on the bottom, a node here on the right, but we're just going to focus in on that node, because KCL says that the flow into a node is equal to the flow out of the node. And so let's go ahead and give that definition then. KCL, the current into a node is equal to the current out of that node. So let's go ahead and label a couple of currents. Now when we label these currents for each of these branches, and so I'm going to call this I1, and then I'll call this one I2, and then we'll call this one coming out this way I3. It's important that we put these arrows here to tell us which direction the current is flowing. And when we give these things values, we know that if it's a positive sign, then the direction of the current, of positive current, is in the direction of the arrow. And if it has a negative sign, it means that the direction of the positive current is opposite the direction of the arrow. And it's okay to have positives and negatives in our answers and in our analysis, as long as we have those arrows drawn. All right, so let me give some values here. So let's say that I1 is 2 amps. And I2 here is 7 amps, and we want to know what I3 is. So we're doing a little bit of analysis. And so in this case, I'm going to say that the current in is equal to the current out, like so. And then I can write these variables. Which ones are flowing into the node? We can see I1 is flowing into the node, I2 is flowing into the node, and I3 is flowing out. So we have I1 plus I2 flowing in is equal to I3 flowing out. Then I can substitute in the values. I1 is 2 amps, I2 is 7 amps, and I3 is unknown. So we can add 7 plus 2, and we can see that I3 is equal to 9 amps. And so I3 here is 9 amps. And so we use Kirchhoff's current law to determine what the value of I3 is. Okay? So let's go ahead and change this a little bit. So if I go ahead and, oh, that's a lot of erasing. That's okay. Go ahead and draw that again. So if I said that I3 instead was pointing in, what would change here? What would be the difference? Well, let's go ahead and redo our expression. So in this case, we would have all three of them pointing in. So I1 plus I2 plus I3 is equal to 0. Now note that the circuit hasn't changed. I still have 7 amps coming in from the right and 2 amps coming in from the left. So I know that there is 9 amps flowing out in the bottom, flowing downwards. But this arrow is pointing upwards. And when we solve this, you'll see we got 2 plus 7 plus I3 is equal to 0. This time I have to subtract the 2 and subtract the 7 from both sides. And we get that I3 is equal to minus 9 amps. So the magnitude is the same. It's still 9 amps, but this time it's flowing out, as we already know, but the arrow for the variable is pointing opposite the direction of the actual positive flow. And so the variable gets a value of minus 9 amps. So there you have it, the importance of drawing our arrows on the diagram, and then a simple example of how we use Kirchhoff's current law to do analysis. I hope you found that to have value for you. I'm Mike Stanzik, and this is Digital Electronics Classroom. Until next time, have a wonderful day.